Hello, Hopewell. This is Mr. Steinberg. We're on day 4 of our e-learning. Today we'll be working on sections 9 and section 10. In our previous sections we found the sums of finites or parts of arithmetic and geometric series. Today we're going to look at something that's a little different, something that's very unique. It's called an infinite geometric series. A geometric series that has an infinite number of terms together. Not every geometric series that has an infinite number of terms can be added together. Only a specific type of infinite geometric series can be added together to make a finite sum. A finite sum just means that the sum does not approach infinity and approaches a specific value or specific number. So the definition at the top of the page says we need to only look at a specific type of geometric series, one that says it converges. So a geometric series can obtain an infinite number of terms and have a finite sum of specific value only if it converges. So our vocabulary word converges, what does that mean? That means that the terms are getting smaller. Every time you add another term, it is adding something to the larger sum, but not a lot, and it doesn't change the value that much because the terms are getting smaller. Well, what makes terms get smaller? If the ratio of the terms has an absolute value that's less than 1. The terms are getting smaller, the sum is getting larger, but not larger by very much when you add smaller and smaller numbers to them. Then if that absolute value of the ratio is less than 1, we say that the series does converge and it has a finite sum. How to find that sum is a very simple and quick formula. It can be found by using this formula. Notice the S that represents our sum doesn't have an index underneath it, which means we're not finding the partial sum of a specific number of terms. This is the sum, an infinite sum containing an infinite number of terms. That's why there's no index down there. It can be found by taking your value of your first term, g sub 1, that's the first term in your series, not sequence, and dividing it by 1 minus your ratio, that ratio that indicates whether it's converging, or the opposite, which we call diverging. Unlike an arithmetic series, this can only happen in a geometric series that is converging. And let's go to the bottom. The very first section we come across, it's going to ask us two things in our directions. It's going to ask us, determine if the series converges or the opposite, if it diverges. When it does converge, we are able to find the sum of an infinite geometric series. So let me just scroll this on up. Let's move this to the top here. I don't want to cover up that formula. We might need that later. So what we're going to do is we're going to look at each of these exercises, determine if they converge or diverge. If it converges, we're going to find the sum of an infinite number of terms. Let's begin with question 1. I take a look at this. We're starting with our first term, then add the second term, third term, fifth term, all the way up to the infinity term. All right, the infinite term at the end, which doesn't exist, but we would just keep adding an infinite number of terms. Let's see, can we do this? Can we use this formula? Does this have a converging sum? I look at this number, the 2.25. That is my ratio. If the ratio does not have an absolute value that's less than 1, then the series diverges. So we are unable to use our formula for this first series. Let's go to the second one, our second exercise. Starting with the 8th term, add the 8th term, add the 9th term, add the 10th term, all the way up to the infinite term at, sort of the end. I can't really call it the end, that's a lie. Take a look at the ratio. Your ratio is -4. If your ratio is -4, it has an absolute value that's bigger than 1, then it does not converge. It diverges, and we can't use our formula to find the sum for this one. Maybe question 3, it says start with, can you see the third term? Add the third term, the fourth term, all the way to an infinite number of terms. This is the first one that has a ratio that has an absolute value that's less than 1. So this is our first series that converges. In order to find the sum, here's what we're going to do. We're going to use that formula. We need to identify what's the first term in the series. So the first term in the series is actually g sub 3, because the index at the bottom indicates that we're doing 3. The third term, we'll do -2 times 4/5 to the third. Now what is 4/5 to the third? 4 to the third is 64. 5 to the third is 125. We multiply that by a -2. And this gives us our value for your first term. So that's -128 over 125. This is the value of your first term in your series. What we're going to do is we're going to write our formula. S equals, I'm going to write -128 over 125, the value of my first term, and divide it by 1 minus my ratio. If I have 1 and I subtract 4/5, I'm left with 1/5. And for those of you who remember how to do this with your keep, change, flip, what we can do is keep, change, and flip the denominator. We can keep the numerator, multiply instead of divide, that's the change, and flip. I'm going to cancel out some of these 5s. Let me use my eraser for a second. I'm going to cancel out some of these 5s here, like the 5 in 125 changes the denominator to 25, and this 5 cancels out. Looks like my solution is negative 128 over 25. What is that? That's the sum of negative 5.12. That's the sum of 5.12. So if I added all the terms up together forever, that sum will approach negative 5.12. Seems impossible, but that's actually true. Let's take a look at question 4. What do you think? Does this series converge or diverge? Taking a look at your ratio. Our ratio does not have an absolute value that's less than 1. This one diverges, and we're unable to find a finite sum. One of our last two is going to converge, and the other is going to diverge. Is it this one? What's taking place in this pattern, in this series? We're adding together, so this is already an expanded one, not in sigma notation. Looks like the ratio, if I take any term and divide it by the previous term, like 6 divided by 3, that ratio is 2. This is doubling. This one diverges. We can't figure out its sum. You take any term divided by the previous, you should get that the ratio is negative 3/4. Since the absolute value of this ratio is less than 1, this is the series that converges. Let's add up all of the terms. The formula for this is the first term value divided by 1 minus my ratio. Okay, something I didn't point out earlier, but I'm going to point it out now. If you're using your calculator to do this, just remember, you want to keep your entire numerator and denominator together, so you use parentheses. I can go back up to the formula and put parentheses around that denominator. Since I didn't use the calculator the last 2 times, maybe I'll use the calculator this time. What I want to do is take the first term, which is a single term. We know its value. I don't need to use a formula, so I'm not going to put parentheses around that. Divide it by 1 minus, now negative 3 over 4. So 4/4 plus a positive 3/4 will be 7/4. 4 divided by 7/4 is this number. So if I did this 4 divided by 7/4, then I would use a keep, change, and flip. I would have 16 over 7. I'm going to use the math button down here and just make sure that this says that it's 16/7 when I change it, and yes, it does. It's 16/7. So the sum of an infinite number of terms in this series will reach 16 over 7. Now the bottom is sort of like an extension of this idea of converging and diverging. If it converges, then it approaches a sum, and if it doesn't converge, well, its sum might be infinite positive infinity, negative infinity, or it may not have any sum that is detectable. And let's take a look at this section at the bottom. The directions say multiple choice. What is the sum of each infinite series? Well, let's do what I'm comfortable doing. Let's take a look at which one I think might have a finite sum. I'm just going to take a look. This is the first one that jumped out at me. Its ratio is 3/4. It looks like it's geometric. Now, this third one looks like geometric also. Which one of these two converges? Well, I think it's this one. This one would converge. Its first term, plug in 1. Its first term would be 7/2, and then it would be divided by 1 minus the ratio of 1/2. So I guess I'll keep, change, and flip. 7/2 divided by 1 minus 1/2. 7/2 divided by 1/2. I'll keep, change, and flip. 7/2 times 2 over 1. These 2's cancel. Now I don't see that this is matching any of these. Maybe this could have been a mistake. I think maybe if the sum said the sum was 7, I would pick this option. So I'm going to just put a question mark. Maybe that was an accident. Maybe I didn't mean to do that. Let me double check. Is the value of the first term 7, or is it 7/2? No, it is 7/2, because when I plug in the value of 1 up here, I do get 7/2. So it looks like I made a mistake when making this packet. Let's take a look at some of the other ones. Now, the first series is arithmetic with a -3 as its common difference, which means, let's plug in, which means the first term is 27, the next term would be 24, then 21, and 18. Now if I add enough of these terms, what's it going to add up to be? I mean, all these terms are positive right now, so maybe I'm thinking it approaches a positive infinity. However, because because the difference is negative, I know these terms are eventually going to go past 0. So you're going to reach 3 and then 0. And then start with the negatives, like -3, -6, and then add a lot more negative terms than there were positive terms forever. I think that the answer to the first one might be letter B, that this is approaching, or the sum will approach a negative infinity if you keep adding terms. Now, here's another reason why I think it. The terms themselves are getting closer to negative infinity, so adding large negative terms will make the sum negative infinity. Let's take a look at this next one. 1 plus -4 plus +16 plus -64. Now these terms are alternating. This has a geometric sequence to it. It looks like our ratio is -4, so it's alternating now. If I add the first term together, it's 1. If I add the first 2, it's -3. If I add the first 3 together, it would be 13, all right, which is a larger positive number than the first one. If I had a fourth term, it would be a negative number. Okay, so this one's sort of oscillating. It's going positive, negative, positive, negative. It just can't make up its mind. This one I think would be impossible to predict because of its erratic pattern. Now, if it had an odd number of terms, I would think the sum would approach positive infinity. If it had an even number of terms, that every even term is an even larger negative number than everything that came before it. It would have a negative infinity pattern or a sum. So I think that would match with D. Now I'm not sure that each of these were used once. Let's take a look at this one. Here our first term would equal 6, then 9. Then I'd multiply 9 by 1.5, so I think that's 13.5, and continue to go down this forever. If I add an infinite number of positive values together, and the numbers themselves are getting larger and larger, I think that, yes, this might be matching with A. So without that little hiccup, we got through our last section, our section 9, before section 10, which is next, which is putting things all together. What can we do with all of our skills? Please continue on in section 10. I'll see you then.